So now let's talk about Charles' Law. I know a lot less about the person behind this particular law. He's actually a Frenchman, and you don't pronounce his name Charles. It's actually Charles. Jacques Charles is the guy's name. And Jacques Charles was actually credited with being the first person to launch a unmanned hydrogen gas balloon back in 1783, and then just a few months later on, he went up in the balloon with another guy named Nicolas Louis Robert, and they flew up over half a kilometer, 1,800 feet up in the air in a hydrogen balloon, and so that's sort of interesting. But Jacques Charles is credited with the discovery of how temperature affects the volume of a gas. He actually didn't formulate the mathematics. Apparently that was this guy, Joseph Louis Gay-Lussac. But Jacques Charles gets the credit for the law anyway. And so Charles' law, the simplest way to think about this one is if you go back and you remember those variables that a gas has. Gases exert pressure, they have volume, they have a temperature, and they have a certain sample size, and we know that today in the term of moles, the number of particles, the number of gas particles, could be molecules, atoms, whatever, those little things that are bouncing around. Okay, so this is the sample. So in Charles' law, he focuses on the relationship between volume and temperature, and he keeps the pressure constant, and he keeps the number of moles, the sample size, constant. And so it's just these two variables, volume and temperature, in the context of this gas law. So we could talk about balloons, that works as well, but I want to draw something hopefully a little bit simpler. Imagine you have a little chamber with a piston inside of it. That's something that can kind of move up and down, kind of like a syringe. And let's imagine you have a constant amount of pressure pushing down on it. So a constant pressure. So this is like a syringe type of thing where it's airtight and you have your sample of gas in here, right? Your gas sample. And so maybe your gas sample is currently occupying 10 liters, okay? And let's say we start cooling that gas down. So we cool it down, and we start noticing something. As we cool it down, let me try it this way so I can try to make it the same size. As we cool it down, we'll notice that the gas sample starts getting smaller. Okay? And so imagine you cool it. Same pressure out here, by the way. We haven't changed the pressure. That's not why the gas is getting smaller here. Constant pressure. But let's say we cool it enough so now that it occupies 5 liters. That's half the volume. And what people like Jacques Charles noticed is there's a quantitative relationship going on here. When we measure the temperature, let's say that this temperature was 290 Kelvin. I have to use the Kelvin temperature scale actually here. And let's say we cool it really, really cold down to 145 Kelvin. That's half the temperature on the Kelvin scale, right? And we notice we get half the volume. And if you think about the reverse process where we heat it, if you could heat it up from 145 Kelvin up to 290 Kelvin to double the temperature, you get double the volume. So when you have half the temp, in Kelvin, by the way, you get half the volume. Okay, and if you start taking down some measurements all along the way, you'll see an interesting mathematical relationship between temperature measured in Kelvin and volume. And it looks just like this. That's called a line. Okay, so if you think about the measurements that you're taking all along the way here, let's say that that's the first temperature, and up here, your second temperature, which is double. What do you notice about the volume? The volume is also double. By the way, Charles' law was actually the inspiration for the discovery of the Kelvin temperature scale. Originally, these measurements were not made in the Kelvin scale. They were made in degrees Celsius. And if you use the degrees Celsius scale for temperature, you get a line that does not pass through the origin, like this one, kind of looks like this. And that's almost, a directly proportional relationship, but somebody thought, hey, what if you went backward and you started cooling the gas and you made the gas as cold as it possibly could be? Eventually, you'd hit a really interesting temperature where it looks like there is no volume, which is very strange. That's almost like the gas disappears. And then negative volume? That doesn't even make sense. How can you have a negative volume of space? This temperature right here, somebody calculated it and they realized that's a really important temperature. It turned out to be negative 273 degrees Celsius, which became absolute zero Kelvin. And so when you change the scale and you put Kelvin on the x-axis, you get a nice linear relationship. And the idea here is volume divided by temperature is a constant. Okay, and that leads to a more convenient form of the equation. It doesn't matter what the volume and temperature are per se, but as long as you keep them paired up, that ratio will be constant. And so this is known as Charles' law. V1 over T1 equals V2 over T2. That's Charles' law. Charles' law. Okay, so let's have a look at some of these Charles' law problems and apply what we've got. A container holds 50 milliliters of nitrogen at 25 degrees Celsius, pressure 736 millimeters of mercury. What will its volume be if its temperature increases by 35 degrees Celsius? All right, so the pressure is constant. They've given us a particular number, but it's constant. So they're not going to change the pressure. What is changing is the temperature and the volume. So we've got an initial volume, 50 milliliters, and it's at 25 degrees Celsius. Now for Charles' law problems, we need to use the Kelvin temperature scale. So we add 273, that's 298 Kelvin. What will its volume be if its temperature increases by 35 degrees? Okay, well, we're going to figure out the new volume. The new temperature is the new temperature, T2, is 25 degrees Celsius plus 35 degrees Celsius, which is 60 degrees Celsius. So 60 plus 273, 333 Kelvin. That's our temperature in Kelvin. So now we plug in V1 T1 equals V2 over T2. And we're going to rearrange this equation for V2. So V1 times T2 over T1. So let's plug in. The first volume is 50 milliliters. The final temperature is 333 Kelvin. The original temperature was 298 Kelvin. Okay. So we're getting a hotter temperature. That means bigger volume. So 50 times 333 divided by 298. Here the units for volume don't matter. We could have used liters or gallons or ounces, fluid ounces. The temperature unit absolutely does matter though. Try that again. Boom. So 55.9 milliliters is our answer. So those are the Charles Law problems. This is called a directly proportional relationship, by the way. Directly proportional relationship. What that means is, as volume goes up, as temperature goes up on the Kelvin scale, as we change that temperature, the volume goes up as well. And as we drop the temperature, the volume drops. Those arrows are pointing in the same direction. Whenever we change the temperature, you get the same type of change in volume. That's Charles' Law. To finish up for today, I would like for you to complete these problems here. I do need to state something about these problems here. Let me see. There's something mentioned called STP. STP stands for standard temperature and pressure. Standard temp and pressure. And for gases, standard temperature and pressure, the pressure is easy to remember. It's 1 atmosphere, standard pressure. Standard temperature for a gas is 0 degrees Celsius. So 0 degrees Celsius, 1 atmosphere, that's standard temperature and pressure. And so if you see STP written anywhere, I'm not sure if we have it in these problems, but for the Boyle's Law problems, that's what STP represents.